So now that we've talked about precision, we can start to think about this extremely important topic called significant figures. And I will comment frequently in your lab reports and in your homework assignments that you're using the incorrect number of significant figures. And I know that oftentimes the math teachers teach that you should always give your answers to 2 places after the decimal or 3 places after the decimal. That's a very arbitrary rule, and it really doesn't make any sense at all. Significant figures exist in the first place because we as human beings cannot measure anything exactly. There is a limit to how precisely we can measure any device. I cannot measure anything more precisely than to the nearest millimeter, or maybe to a small fraction of a millimeter with a meter stick. Things smaller than that, or to achieve a level of precision better than that, is just not possible with that device. There are other devices that I could use that would be able to give me more precision, but the idea of significant figures is that if you make a measurement, you should not express more than you actually know. And so I gave an example with the precision where I measured to 6 places after the decimal, but that's impossible to do with the meter stick. So I ended up eliminating some of the ones that I thought might have existed and only kept the ones that I really knew were actually true. So significant figures are a way of expressing what we actually know and nothing more than that. It's very important that you don't misrepresent data and make it seem like you measured something more precisely than you really did. So in any number, to give you an example, the first number is the most significant because it represents the largest portion of a measurement, and then the last number is the least significant. So just to give an example, if I pick the number 205.63, the most significant number is right here. Because of this number, 205, that 2 represents the 200 part. The remaining is only 5.63. So this 2 represents the largest portion of the number, and of course, therefore, it's the most significant number in this measurement. The least significant one is this one because it represents a very small part, only 0.03 of the measurement. It's not even 1% of the measurement, whereas the 200 represented more than 90% of the total 205. So this is my least significant figure. Okay, so that's pretty simple. Now, there are rules for knowing whether a number is considered to be significant or whether it's not to be considered significant, and these are the 4 rules that you will need to remember to determine whether a number is significant, and then we'll look at the math. When you do math with significant figures, there's rules for how many numbers can you keep, even though your calculator may say more or less. So for the first rule, all non-zero numbers are significant. So if we go up to our previous example that I gave you, 205.63, the 2, the 5, the 6, and the 3, no doubt those are significant figures. The second rule, and this is a no-brainer, if they are non-zero numbers, then they're significant. The confusion always comes with the zeros. Sometimes the zeros count, sometimes they don't. The simplest one is zeros that are between non-zero numbers, those are significant. So, for example, that 0 between the 2 and the 5, that clearly is a significant figure. It's between 2 non-zero numbers. That counts. I put a 0 there, not because I don't know what the number is, but because I do know what the number is, and the number is 0. The third rule, all final zeros after the decimal place are significant. So if I had a 0 at the end after here, that would be considered a significant figure because, again, I'm not putting a 0 there because I don't know what the number is or because I think it's a 0. If I put a 0 there after the 3, it's because I know that the number is actually 0. May not know what the next number is, what the next place after the decimal is, but that next one there, if I put a 0 there, what I'm saying to the reader who's reading the lab report is that I know the value of that number to be 0. The fact that I did not record any numbers after that indicates that I don't know about the numbers after that. The last rule, number 4, and this is the one where people tend to run into the most confusion, zeros that are used only for spacing the decimal point are not significant. So I think the easiest way to think about that is we'll look at some examples. So I have 8 examples and the 4 rules. Okay, so let's take a look, and using these 4 rules, we'll determine how many significant figures exist in each of the numbers. So 23.45, no zeros in there, all non-zero numbers. This one has 4 significant figures. Number 2, 204.56. There is a 0, but it's between 2 non-zero numbers. Of course, the non-zero numbers count, but because this is between non-zero numbers, that also counts as a significant figure. So I have 5 significant figures in that number. And remember, these are not numbers that just were made up. These are numbers that, in theory, would have been produced by some measurement. We would have measured some device or some object and come up with this number, and it represents what we really know, not what we don't know. So number 3, 23.700. The 2, 3, and the 7, no doubt, those are significant figures. The 2 zeros, all final zeros after the decimal, are significant. If a person tells you that these 2 numbers are 0, they are telling you that because they know that to be true, not because they think they might be, or maybe they're very small numbers. If you put a 0 there, it means you know the value of that number to be 0. It's not a 1, not a 2, not a 3, it's a 0. So in this case, these 2 zeros do count, and I again have 5 significant figures. Question number 4, or example number 4, 2700. Now this one is a little bit different. This said all final zeros after the decimal are significant, but there's no decimal here. So are these 2 zeros considered to be significant? This one falls under the rule for number 4. Zeros used only for spacing the decimal point are not significant. So if you could imagine, for example, that I were to remove those 2 zeros, that would change the value of the number from 2700 to only 27. So in this case, I'm not saying that these zeros are the values for the numbers. I have to put something there. I have to put something to fill the space so that you know where the decimal point is. That 2 is in the thousandths position. The 7 is in the hundredths position. You wouldn't know that if I didn't have the zeros after that. So in this case, since these zeros are only being used to space the decimal point, to tell me where the decimal point is at, this one has only 2 significant figures. Let's look at another example of this. Example number 5 also has a lot of zeros that are not considered significant because, again, they simply are placing the decimal point, 0.000458. Now the 458, no doubt, significant figures. But these zeros and the one in front, do they count as significant figures? Again, zeros used only for spacing the decimal point are not significant. If I remove them, this number goes from being 455 ten thousandths, to 458, sorry. So in this case, those zeros are not considered significant. They're there to show me that this 4 is not in the ones, it's not in the tenths, it's not in the hundredths, the thousands, it's in the 10,000ths position. And without putting that decimal and having these zeros as placeholders to tell me where the 4 is actually located, it would change the value of the number. So in this case, we have only 3 significant figures. Okay, so now let's combine together some of the rules and take a look at some more complicated versions of these. 2074.080. So we have 2, 7, 4, and 8. That's 4 significant figures. They definitely count, but the question is the zeros. Well, this one is between 2 non-zero numbers. This 0 is between 2 non-zeros. And this 0 is a final 0 after the decimal place. Okay, now that's very different than these zeros. These are not the final zeros. So that hopefully is very clear. These are not final zeros. These are final zeros. These are not considered final zeros because they're there to tell you where the decimal place is. They have to be there. There's no way to write this number in this format without putting the zeros there. Now there is a way to write this number without using the zeros, but as it's written without the decimal place, the zeros are not considered to be significant. So because this one is a final 0 and it's after the decimal place, this does count as a significant figure, and that means in this one we have 7 significant figures. Okay, so let's look at example 7. 0.040506. Now the first two zeros are there to tell you where the decimal place is. So these are not going to count. They're not final zeros. They're simply there as placeholders to place the location of the decimal point. This 0 is between two non-zero numbers, and this 0 is between two non-zero numbers. So those two zeros get counted as significant figures. And that means that for this one, I would have 5 significant figures. Okay? One last example. 20,320. The 0 between the 3 and the 2, no question, that's a significant figure. That 0, does it count as a significant figure? It's not after the decimal place, so that rule is out. And if I took that 0 away, it would change the number to 2032. So that 0 is not there because I know it. It's there as essentially a placeholder so that I can place the decimal place. I know the decimal place is here. The 2 is in the 10,000s place. This is in the thousands, the hundreds, the tenths. I don't know the value of the ones. So in this case, I have 4 significant figures. Okay? Now, there's actually a trick when you have these zeros that are here as placeholders. There's sort of a trick for doing this so that you only show the figures that are actually significant, and that is that you use scientific notation. So rather than writing 2700, it would be preferred, and you will see this frequently in the book, that they use scientific notation for numbers that are fairly small. I'm sure you've been taught that scientific notation is about dealing with big numbers. Instead of writing out long 6, 10, 20-digit numbers, you use scientific notation because it makes it a little more compact. But actually, scientific notation is used for other things than just making numbers smaller. It's used also to express significant figures, the ones that we really know are valid. So in this case, I would write 2.7. Those are the two figures that are actually significant, and then I would write times 10 to the, in this case, I'm moving the decimal place to 3 places. This is a more accurate way of expressing the number 2700 and stating to the reader that you only really know that the first two numbers are accurate. Similarly, the number down here at the bottom, this 0 is a placeholder. So what I could have done was said 2.032 times 10 to the, and now I'm going to move 1, 2, 3, 4 places. So it's 2.032 times 10 to the 4th. And now you can see it's very clear there are only 4 significant figures. With scientific notation, I don't need to have zeros as placeholders because this 10 to the 4th is going to tell me where the decimal place is supposed to be. So this is a little trick that makes it a little more accurate. Now it not only works for big numbers like this, you could also do it for small numbers. So here we had a small number that had some placeholders also. These zeros are here as placeholders. I could have written this as 4.58 times 10 to the, now in this case I moved the decimal place in the other direction. So I went 1, 2, 3, 4 places, but because I went in the opposite direction, I would say 10 to the negative 4th. Right? And that 10 to the negative 4th means that when you write this number in long form, you would move the decimal to the left. I could just as easily have done it for this number, 0.040506. I would write that as 4.0506 times 10 to the 1, 2, to the minus 2. So in these cases, it's preferred that you write the numbers in scientific notation because it makes it more clear. Now here, there's no doubt. These zeros are not significant. They're not significant for sure. Here, it's a little less clear. Maybe you really do know the numbers, but you don't know the next one, right? The point, what's the number here? If you knew it was 0, then you would write 2700.0, and all these zeros would then count. But in this case, because I don't know what the next number is, I have to somehow express that the number is in the thousands, but yet I only really know the first two numbers are actually true. So this is why scientific notation really comes in handy. You'll see it in the book. Oftentimes answers that are small answers. 2700 is not a big number. It would not usually be written in scientific notation, but because we want to express only the numbers we really know, that's why we're going to express it in scientific notation.